Bismillahirrahmanirrahim. Assalamu alaikum. So today is our 10th lecture, but I am recording this lecture in two parts. So today I am recording lecture 10A and then I'll record lecture 10B. So lecture 10 is divided into two parts, 10A and 10B. So this is 10A. So in this lecture, we will start from the quadratic residue. In last lecture, we discussed about the quadratic congruence, and we discussed that quadratic congruence x square is congruent to a modulo p. Okay. So we discussed two types of two different quadratic congruences. One was one was simply y square is congruent to 10 modulo 13, and this congruence was solvable, and the solution is y is congruent to 6 and 7 modulo 13. So 6 and 7 are the solutions. Okay. Modulo 13. Okay. And we have already discussed that any congruence of the form ax square plus bx plus c is congruent to 0 modulo p, okay, can be converted into this form y square is congruent to any number, for example a prime modulo p. Okay, so if we are able to find the solution for y square congruent to a prime modulo p, then we will be able to find the solution for ax square plus bx plus c is congruent to 0 modulo p. Okay, so and that thing has already been discussed in the last lecture. Okay, so that this congruence is solvable, and the solution is 6 and 7. If we put 6 here, we get 6 satisfying this congruence and 7 also satisfying this congruence. But we discuss another congruence, and that was y square is congruent to 2 modulo 13, and we discussed that there was no solution. Okay, no solution, because we will not be able to find the value of y in Z13 so that we get 2 here. Okay, so that's the problem. So this quadratic congruence is not solvable. Okay, so today we will study that which type of congruence are solvable and which are not solvable. Okay, if we look at the numbers here, okay, so we have 10 here. So if we have 10, so this equation, this congruence is solvable. And if we have 2 here, so this congruence is not solvable. Okay, so the important thing is the quadratic residues. So if the congruence, quadratic congruence is solvable, then this number is a quadratic residue. And if the quadratic congruence is not solvable, so it means this number is not quadratic residue. So it means 10 is a quadratic residue of 13, while 2 is not the quadratic residue of 13. Okay. So in 13, in modulo 13, we have 1 to 12 non-zero numbers or 12 non-zero integers. Okay. And some of them are quadratic residues, and some of them are not quadratic residues. And we will see that which of them are quadratic residues and which of them are not quadratic residues. Okay. So look at the equation. For example, we consider x square congruent to a modulo 13. Okay. So if we put a from 1 to 12, okay, so there are 12 non-zero integers from 1 to 12. Okay, so which of them are quadratic residue and which of them are not quadratic residue? So if a is such a number, in that case this quadratic congruence is solvable, then that number is called quadratic residue. And if the quadratic congruence is not solvable, then the integer is called non-quadratic residue. Okay. For example, if you look at 1, okay. So for the case 1, so if we take a is equal to 1, okay, so x square is congruent to 1 modulo 13. So in this case, this quadratic congruence is solvable, okay, because if we put x equals 1 here, okay, or 12. So in this case, x is equal to 1 and 12 are the solutions. Okay. So 1 is a quadratic residue, while 2 is not quadratic residue, because we will not be able to find any number, okay, which is the solution of the quadratic residue when we write x square is congruent to 2 modulo 13. Okay, so 2 a is equal to 2 is not a quadratic residue, so non-quadratic residue. Similarly, if we take a equals 3, so x square is congruent to 3 modulo 13. Okay, so if you uh, look at the quadratic congruence, so if we put x equals because we have 3 here, so 4 square is 16, so which is 3 in modulo 13. So 4 is the solution as well as 9. So x equals 4 and 9 modulo 13. So this is the solution. Okay. So similarly, we have so 1 is a quadratic residue. So 1 is a quadratic residue, so it means 1 square or 12 square is a solution. 2 is not a quadratic residue. 3 is a quadratic residue. So 4 square or 9 square is a solution. 4 or 9 is a solution because 4 square is 3 and 9 square is also 3. Okay. 4 is also a quadratic residue because 2 square is 4, or it's better to use congruent sign, and all of them are modulo 13. Let me write modulo 13 combined for all. Okay, all of them are for modulo 13. So 2 and 11. Okay, and then 5 is not a quadratic residue, 6 is not a quadratic residue. You can verify easily. 7 is not a quadratic residue, 8 is not a quadratic residue, 9 is a quadratic residue because we can write 3 square, and this is same as 10 square because, and 10 is also a quadratic residue because 6 square is 36. 36 is 10 in modulo 13, and 7 square is also quadratic residue. And similarly, if 1, then 12 as well. So 12, so 12 means 5 square or 8 square. So these are all quadratic residues. So quadratic residues are 1, 3, 4, 9, 10, 12. Okay, so these 6 integers are quadratic residues of 13, and the remaining 6 are not quadratic residues of 13. So which are 2, 5, 6, 7, 8, and 11. So these numbers are non-quadratic residue and these numbers are quadratic residues. So if we have a quadratic congruence for modulo 13, then if A is one of them from the quadratic residue, then this quadratic congruence is solvable. Otherwise, quadratic congruence is not solvable. Okay, so that's the important thing. And if we look at the non-zero elements of modulo 13, okay, or Z13 star, we know that Z13 star is Z13 star is Z13 minus 0. Okay, so there are 12 elements, and so these 12 elements are partitioned by the quadratic residues. For quadratic residues, let me use QR. And for non-quadratic residues, let me use NQR. So quadratic residues are 1, 3, 1, 3, 4, 9, 10, and 12. And quadratic non-residues are 2, 5, 6, 7, 8, and 11. So these are the non-quadratic residue, and this set Z13 is partitioned by quadratic residues and non-quadratic residues. Okay. So now we know that quadratic congruence is solvable when A is a quadratic residue, and not solvable if A is not is if A is a non-quadratic residue. Okay. So look at the quadratic congruence. X square is congruent to A modulo P. Okay. So we have this congruence, quadratic congruence. Okay. So there is a lemma. Suppose A is a quadratic residue. So if x square congruent to A modulo P is solvable. Okay. If x square congruent to A modulo P is solvable, then the congruence has exactly two incongruent solution. Okay. So that's the statement of the result. If x square congruent to A modulo P is solvable, then the congruence has exactly two incongruent solution. Okay. So proof. So it is given that the equation is solvable or congruence is solvable. So let alpha be a solution. Okay. Then solution of x square congruent to A modulo P. Then alpha square is congruent to, because if alpha is a solution, that it means alpha must satisfy this congruence. So alpha square congruent to A modulo P. Okay. Let another element beta, which is equal to P minus alpha, then what is the value of beta square? Value of beta square under modulo P. Okay, then we take a square here. So P minus alpha square. So P minus alpha square under modulo P. So because we have P minus alpha whole square, so that will be P square minus 2P alpha plus alpha square. So because P becomes 0, we are taking modulo P. So we don't need to apply formula. So we just put 0 here. So we can write minus alpha square is congruent to alpha square, and this alpha square is congruent to A modulo A modulo P. Okay, so we have assumed that alpha is a solution of quadratic congruence, and we assume another number beta which is equal to P minus alpha, and this element beta which is equal to P minus alpha is also satisfying this congruence. So it means beta is another solution of the quadratic congruence. But we have to show that only two incongruent solutions. So thus beta is the second solution. Okay. One more thing, we are considering odd prime. P is a prime, but P is odd prime here. Okay. Throughout our in throughout our lectures. So P, if P is an odd prime, okay, so P minus alpha is not equal to alpha again, because the GCD of P and 2 will be 1. Okay, so it means alpha and beta are two incongruent. Okay, because okay, so here we have GCD of 2 and P is 1. So it means P is not equal to 2. So it means P minus alpha is not equal to alpha. So beta is different from alpha. So we can write thus alpha and beta are two incongruent solutions. Okay. Now we have to show that there are exactly two solutions. It means if there exists a third solution, and that third value must be either equal to alpha or beta. Okay. So let to show that there are exactly two solutions, we assume that gamma be the gamma is the third solution. Okay, we assume that gamma is a third solution, so it means gamma must satisfy the equation. So gamma square is congruent to A modulo P, or one can write gamma square is congruent to alpha square congruent to A modulo P. Okay, because gamma is also a solution, because if beta is a solution, so beta square is congruent to alpha square congruent to A modulo P. So if gamma is a solution, then gamma square is congruent to alpha square congruent to A modulo P. Okay, so P divides gamma square minus alpha square. Okay, so if P divides gamma square minus alpha square, then gamma square minus alpha square can be written in the factors. So P either divide gamma minus alpha or gamma plus alpha. Okay, so if P divides gamma minus alpha, so if P divides gamma minus alpha, then gamma is congruent to minus alpha, which is congruent to beta, congruent to beta modulo P, and if P divides, so this is plus alpha. Let me write plus here. So if P divides gamma plus alpha, then gamma congruent to minus alpha, which is congruent to beta modulo P, because beta is P minus alpha, and P minus alpha in modulo P is minus alpha, same as minus alpha, or congruent to minus alpha. So if P divides gamma minus alpha, then gamma is congruent to alpha modulo P. So it means if gamma is the third solution, so that must be either equal to alpha or beta. So it means there are exactly two incongruent solution of a quadratic congruence if quadratic congruence is solvable. Okay, so in quadratic congruence is only solvable when we have this A equal to a quadratic residue of P. So if A is a quadratic residue of P, then the quadratic congruence is solvable. Okay. So inshallah, we will discuss next result, which is Euler's criterion, in the second part of lecture 10A. Okay. Allah Hafiz.